So this is the advanced tutorial for our solids and fluids. We have a diving bell lowered into the ocean, and the absolute pressure outside the bell is 1438 kilopascals. We want to find the depth of the diving bell below the ocean surface. Okay. And we have our bell here, and we know that the pressure is equal to 1438 kilopascals, and we want to find the height, right? And we've been told that the pressure, the atmospheric pressure, so at the surface of the water, the atmospheric pressure is 101 kilopascals. Okay. So that's the information that we have. So it doesn't seem like a lot, but so what you can do is you can calculate the difference in pressure between this depth here and the atmosphere or the surface. So we can calculate the delta P. So that's going to be 1438 kilopascals minus 101 kilopascals. So that's going to give you 1337 kilopascals, or 1337 times 10 to the 3 pascals. Okay, so if you have the difference in pressure, you can now use this equation. So delta P is equal to rho G delta H, right? So we're just going to rearrange this equation for delta H. Delta H is equal to delta P divided by rho G. So that's 1337 times 10 to the 3 over our density of seawater, which is 1030 times 10, and that will give you 130 meters, or 129.8, which rounds to 130. Okay, so not that hard once you know what to do. Number 2 is quite a tricky one. I got stuck on it tonight for a while. I was trying to remember how to do it, and I couldn't remember. But I figured it out in the end. So number 2 is a hard one. A solid sphere is completely submerged in water, and it's released. And when it's released, its acceleration is 10 meters per second squared upwards. And so we want to, and that the acceleration is 10 meters per second squared. We want to know what the density of the sphere will be. And we were told that the density of water is 1,000 kilograms per meters cubed. So here's our sphere. We have, so we're going to have the forces that are going to be acting on the sphere, right? We're going to have a buoyant force. So FB, that's our buoyant force that's pushing this sphere up, right? Because you've displaced water and the water wants to push it out. So we have that force. And then we're also going to have the weight force. So this is due to gravity, right? And then you're going to have the net force. So after you add the buoyant force and the weight force, you'll be left with the net force. So this is net force. And obviously, because it's accelerating upwards, that means that the buoyant force must be greater than the weight force because it's accelerating towards the surface. So our net force is also going to be in a upwards direction, right? Okay. This one's a lot of maths, and don't be too worried if you don't get it. It is quite tricky. So first of all, we're going to say that upwards is positive and down is negative, okay? So then our acceleration is positive 10 meters per second squared, and that means that gravity will be acting in the opposite direction, downwards. So that's going to be negative 10 meters per second squared. And also what you should know is that so mass is equal to the density times the volume, okay? So here we want to find out the density of the object. So whenever we have force is equal to mass times gravity, instead of using mass, we're going to use density times volume times gravity, okay? So we've replaced m with density and volume, okay, because we're dealing with liquids here. And unless we do this, we can't figure out the density of the object. Okay, so we're now going to put this into an equation. So this net force here is what's causing the acceleration, okay? So we can say that the net force is equal to mass times acceleration. But of course, we're not going to use mass. We're going to use density times volume times acceleration. So, right, and then we're going to say that the net force is equal to the buoyant force plus the weight force, okay? And the buoyant force will be acting in an upwards direction, and the weight force will be acting in a downwards direction. So the equation for buoyant force is the density of the liquid multiplied by the volume of liquid that has been displaced. And because the object is fully submerged, that's going to be the volume of the object. So the volume of the object, which is equal to the volume that's been displaced, times gravity. So this is the buoyant force here. And so what would happen, I'll just finish this and then, so the weight force is going to be mass times gravity, but that's going to be density of the object multiplied by the volume of the object multiplied by gravity. Okay, so this is the buoyant force and this is the weight force. Okay, so we know that the buoyant force is supposed to be acting in an upwards direction, but if you put in g, which is negative 10, that would give this part here a negative value, which isn't right. So this is just going to give you the magnitude of this force, of the buoyant force, but we have to use, for this one here, we have to use the value of positive 10, because we're just using the g value to calculate the magnitude. So I'm just going to put here g subscript up to remind us that this g here should be positive 10, not negative 10. because the force is acting upwards, whereas this force here we can use -10 because that's acting downwards. It's this one here. Okay. Right. So F net force, that's going to be the density of the object times the volume of the object times the acceleration of the object, and that's equal to the density of the liquid times the volume of the object times gravity up plus density of object, volume of object times gravity. Okay. So here we've got the volume of the object, which is in every term. So we can now cancel out volume object because it's a common factor in all of our terms. So we don't need that anymore. So you're going to rub that out. Okay, and then what you want to do is you want to get, so I'll just write this again, sorry. So density of object times acceleration is equal to density of liquid times gravity up plus density of object times gravity. Okay, so we want to get the density of the object both on the same side. Okay, so that's going to become, we're going to minus density of object from both sides. So then density of object times acceleration minus density of object times gravity is equal to the density of the liquid times gravity up. Okay, so then we're going to now factorize A and G. So density of the object times A minus G is equal to the density of the liquid times gravity up. Okay, so we want density of object on its own. So we're going to divide both sides by A minus G. So density of object is equal to density of liquid times G up over A minus G. Okay? So now we'll put in the numbers. So density of object is equal to density of liquid, which is 1,000. And so G up, so that's going to be positive 10, right? Because that was acting in the upwards direction. And then acceleration is positive 10 minus our G value, which is negative 10. So if you minus a negative value, that's just plus. So that's 10 plus 10. So that's going to be 10,000 over 20, which is equal to 500 kilograms per meter cubed. Okay? Cool. I mean, like, to be honest, if that came up in the exam, I probably wouldn't have solved it. So number 3, a beaker is filled to the brim with water and placed on an electronic scale. The beaker filled with water weighs 800 grams. A sphere of some unknown metal is gently lowered into the beaker until it rests on the bottom of the beaker. During this process, 50 grams of water is spilt out of the beaker, collected and removed from the scale. The scale is now seen to read 900 grams. What's the density of the unknown metal? So we've got so a sphere of unknown metal is now in our beaker, and our beaker was filled with water, but when the sphere was put in, some water spilt out, which was collected. So this is the water that has spilt out, and so we know that the mass of the water spilt is equal to 50 grams, right? So we have to convert 50 grams. Oh, no, let's just write down 50 grams for now, okay? So we'll just write down 50 grams. That's the mass of the water that's spilt. And so what we can do now is we can calculate the volume of this water that was spilt, because we've been told the density of the water, right? So the density of water is equal to 1,000 kilograms per meters cubed. So volume of the water spilt will be equal to the mass of water divided by the density of the water. So V equals M over rho. So for this one, we'll have to, so this will be 50 times 10 to the negative 3 kilograms, okay? Or you could just say 0.05, so 0.05 kilograms over our density, which is 1,000. So that's just going to be 5 times 10 to the negative 5 meters cubed. So that's the volume of water that has been spilt. And because our beaker was filled to the brim, this must be equal to the volume of the sphere. So now we know the volume of the sphere. So the volume of the sphere is equal to 5 times 10 to the negative 5 meters cubed. Okay? So now we know the volume of the sphere. And what we then need to calculate is the mass of the sphere. So how much water is going to be in this beaker right now? So we had, initially we had, so the mass of water initial was equal to 800 grams, right? And then the mass of water after the sphere was put in. So if you spilt 50 grams of water, how much would be left in the beaker? Yep, 750 grams of water is now in the beaker, but the scale says that the scale says it's now 900 grams. So then how heavy would this sphere have been? Yeah, 150 grams, right? So the mass of the sphere must be equal to 150 grams. Okay? Because we know there's only 750 grams of water in the beaker, but it now weighs 900 grams in total. So the sphere must be 150 grams, which is equal to 0.15 kilograms. Okay, so now we have the volume and the mass, we can calculate the density. So the density of the sphere will be equal to the mass of the sphere divided by the volume of the sphere, which is equal to 5 times 10 to the negative 5 over, sorry, my bad, got mixed up, 0.15 over 5 times 10 to the negative 5. So that should give you, where are we, 3,000 kilograms per meters cubed. Okay? Sweet. So that makes sense, right? Because we spilt 50 grams of water, but the sphere was 150 grams, so the density would be 3 times the density of water. So it all makes sense. Number 4, oil, a viscous fluid. So viscous, we're going to use that equation. It flows out of a tank through 2 pipes, and the flow is laminar. The pressure difference between the ends of the pipe is the same for each and does not depend on length. So what that means is that delta P1 is equal to delta P2, right? The pressure difference between the ends of the pipes is the same for each and does not depend on length. Pipe 2 has twice the diameter of pipe 1. So remember that if it has twice the diameter, it means that it also has twice the radius. Okay, so that means pipe 2, the radius of pipe 2 is equal to double the radius of pipe 1, so 2 times the radius of pipe 1. Okay, so R2 is equal to 2R1. And we don't know the lengths of pipes 1 and 2, but what we do want to ensure is that the flow rates of both the pipes are the same, and we're going to do that by adjusting the length of pipe 2. Okay? And so which one of the following best describes the required length of pipe 2? So for this one here, we can't just actually go through the options one by one because it doesn't really work like that for this one. We have to calculate it. So, and also what we need to do is flow rate 1 has to equal flow rate 2. Okay? And we know that flow rate is equal to delta P times pi times r to the 4th power over 8 times the viscosity times the length. Okay, so now we're going to say replace flow rate 1 with this here. So that's going to be delta P1 times pi times r1 to the 4th power over 8 times n viscosity 1 times length 1 is equal to delta P2 times pi times R2 to the 4th power over 8 times viscosity 2 times length 2. Okay, so that's flow rate 1, flow rate 2, and they're equal. And so we know that delta P1 and delta P2 are the same, so we can cross this one out. We know that pi is going to be the same. We know that 8's the same. We know that the viscosity is the same because it's the same oil flowing through the pipes. So the only ones we have left is R and L. So now you have R1 to the 4th power over L1 is equal to R2 to the 4th power over L2. Okay, and remember that R2 is equal to 2R1, so now we're going to replace it. R1 to the fourth power over L1 is equal to R2, which is 2 times R1 to the fourth power over L2. Okay, so whenever you have an exponent outside brackets, the exponent is going to be applied to both of those, everything that's inside the brackets. So that's going to be 2 to the power 4 times R1 to the power 4 over L2, right? So now we have R1 to the power 4 on both sides, so those can cancel out. So we're going to cancel out R1 to the power 4 because they have the same value. And so that means that we're left now with, so I'm going to use a different colored pen here just so you don't get confused here. We've got nothing on the top, so that just becomes a 1. 1 over L1 is equal to 2 to the power 4 over L2. Okay. So we're going to flip it upside down so that we get L2 on the top. So L1 over 1 is just L1. So we're going to just say L1 is equal to L2 divided by 2 to the power 4. And we want to have it as L2 equals something. So we're going to move this to the other side. So then L2 is equal to 2 to the power 4 times L1. And 2 to the power 4 is going to be 16. So L2 is equal to 16 times L1. Okay, so what you saw there was that because pipe 2 has twice the diameter, the flow rate, so if you look at the equation here, if you double the radius, it's going to increase the flow rate by 16 times. Okay, so if you have a viscous fluid and you double the radius, it's going to increase the flow rate by 16 times. And if you, you guys haven't covered it in Hubs yet, but I think in semester 2, Hubs 192, you learn about, you actually use, you have to understand this equation, because when you control the blood flow to certain parts of your body, the blood vessels, they dilate and they constrict. So they change their radius, and so a very small change in radius will result in a very big change in the blood flow, the flow rate, right? So this is why you have to understand, this is how physics applies to other papers like Hubs, and when you try and understand how the body works, so physiology. Yeah. Cool. So number 5 we went through in the last tutorial. So we'll go to number 6. We have a volume of viscous liquid to be injected into a patient, and a needle with a diameter that is 30% greater than the usual needle is used. So again, we're going to use that viscosity equation. So flow rate is equal to delta P times pi r to the fourth power over 8 times viscosity times L. And we know that a needle with a diameter that is 30% greater than the usual needle is used. So the radius will be 30% greater as well. So the new radius, so we'll call that R2, is going to be 30% greater than R1, which is the original needle or the original radius. So 1.3 times, that's going to be saying that it's 30% greater than R1. Okay? So R2 is equal to 1.3 times R1. Sorry? Because if it was 0.3, then that would mean that it's only 30% of the original radius. So it's the original radius, but it's greater than the original radius, 30% greater. So it has to be the radius plus 30%. Yeah. So if you had, let's say R1 is equal to 1, right? Okay. So if you did R2 is equal to 0.3 times 1, that would be equal to 0.3, right? But if you did R2 is equal to 1.3 times 1, that's 1.3 meters, which is 30% greater, right? Okay. And then, so the normal needle injects the desired volume in 20 seconds. So normally, the time, so T1 is equal to 20 seconds. Okay. And then the pressure difference between the ends and the length of the needle are the same in both cases. So that means that the pressure difference, so delta P1 is equal to delta P2 because there's no change. And the length of the needle is the same, so L1 equals L2. And so how long will it take to deliver the desired volume with the new needle? So we're looking for the new time, which is going to be T2. So T2 is equal to question mark. So now we need to use the viscous equation, but we need to have time in there. So we need to have the variable time. And the way we're going to do that is to replace flow rate. So I told you to write down this one here, which was the change in volume over time, right? So now we're going to use this version of the viscosity equation. So now we have the time variable. Okay. So now we have to actually rearrange this equation for something that stays the same in both needles. Okay. So we could choose to use rearrange for delta P, or we could rearrange for the length. But because delta P is on the top, so it's going to be easier to just rearrange for this one. So what we're doing here is we're rearranging for something that's going to stay the same. Okay. So we'll do that. So I'm just going to skip straight to the rearranged thing. So this will go to the top. So delta V times 8 NL over, that goes to the bottom, T pi R to the fourth power. Okay, so this is our new rearranged equation. And we know that delta P1 is equal to delta P2. So that now means that delta V1 times 8 times viscosity 1 times L1 over T1 times pi times R1 to the fourth power is equal to delta V2 times 8 times viscosity 2 times L2 over T2 pi times R2 to the fourth power. So this is delta P1, this is delta P2. Okay, delta P1 equals delta P2. Okay? I know I'm repeating myself a lot, but I just want to make sure that you guys get it. Okay, so again, we're going to now look for the ones that we can cancel out to make it simpler. So we know that length 1 and length 2 are equal, so we can cross out length 1 and length 2. So the viscous liquid doesn't change, it's the same liquid, so the viscosity won't change. We can cross that out. 8 is going to be the same. We're going to inject the same amount of desired volume. So V1 and V2 will be the same. Pi is going to be the same. So now the only things that we have left over is T and R, right? So now we have, so there's nothing on the top, so that's just going to be 1 over T1 times R1 to the 4th power is equal to 1 over T2 times R2 to the 4th power. Okay, and we're going to flip both sides over to make it easier for ourselves. So that's just going to be T1 times R1 to the 4th power is equal to T2 times R2 to the 4th power. And we want to get T2 on its own. So we want to get T2 on its own, so we're going to divide both sides by R2 to the 4th power. So that's T2 is equal to T1 times R1 to the 4th power over R2 to the 4th power. Okay, and then remember we said R2 is equal to 1.3 R1. So now we're going to make that substitution. So R2 is equal to 1.3 R1 to the power of 4. So that's T1 times R1 to the 4th power over 1.3 to the power of 4 times R1 to the power of 4. We have R1 to the power of 4 on the top and the bottom, so they can cancel out. Okay. So, and then we know that T1 is equal to 20 seconds. So 20 divided by 1.3 to the power of 4 is going to be T2. So that will be 7 seconds. Okay? So you can see that even though we only increased the radius by 30%, which is not a big increase, we've decreased the time to inject the same volume by quite a bit. So we went from 20 seconds to 7 seconds. So our flow rate has increased quite a lot, even though we haven't applied any more pressure. So next one, again, it's a viscosity problem. Viscous fluid flowing into a bucket through a long hose takes 5.3 minutes to fill the bucket. If the diameter of the hose was reduced by 10% and all other conditions are held constant, how long would it take to fill the bucket in minutes? So now we have T1, so the initial time. T1 is equal to 5.3 minutes. We have to turn that into seconds. So that's 5.3 times 60, which is equal to 318 seconds. So that was our T1. And then, so the diameter of the hose is reduced. So that means the radius of the hose is reduced by 10%. So R2, the new radius, is equal to 0.9, right? So 10% less is 0.9 times the initial radius. And we want to find out what the new time will be, which is T2. So T2 equals question mark. So the only things that are changing here is the time and the radius. So this is exactly the same as the last equation, the last problem. So we're just going to skip to the part where we had T1 times R1 to the 4th power is equal to T2 times R2 to the 4th power. So as you can see, it does come up multiple times in the past exams, so it might be worth putting on your cheat sheet just T1, just this equation here, because if the only thing is changing in a viscous fluid is the time and the radius, then you can just jump straight to this equation here instead of doing the long rearranging things and cancelling out that we did before. Okay? So I'd recommend that. Just chuck this on your cheat sheet. And you can use this if viscous fluid and only time and radius change. Okay, so we want T2 on its own. Just going to go through this a little bit faster. So T2 is equal to T1 times R1 to the power 4 over R2 to the power 4. So T1 is 318 and R1 to the 4th over, so that was, R2 was 0.9 R1, which is going to be 0.9 to the power 4 times R1 to the power 4. Right, so I've just skipped the intermediate step, but it's exactly the same as the last one. So then we can cancel out the R1s because that's going to be exactly the same. So 318 divided by 0.9 to the 4th power, and that's going to give you 484.68 seconds. You want the answer to be in minutes, so you'll just divide that by 60, which will give you 8.07, which is 8.1 minutes. Okay, so number 8 was something that I covered in the last tutorial as well, so we'll skip over that one. So number 9 on the last page, we have a 1 meter long pipe with a radius of 1 centimeter, and we're using that to measure the viscosity of an unknown fluid. To do this, a constant pressure difference is maintained between the ends of the pipe. It takes 30 seconds for a volume of water to flow through the pipe, but 75 seconds for the same volume of the unknown fluid to flow through the pipe. What is the viscosity of the unknown fluid? So we're using the same pipe both times. So first we have one pipe, and then first we're going to put water through it, and then the second time we're going to put our unknown fluid through it. So the length of the pipe doesn't change. So we're going to use that viscosity equation. So L1 is equal to 1 meter, and L2 is also equal to 1 meter. So L1 equals L2. The radius is 1 centimeter, and that also doesn't change. So R1 is equal to R2, which is equal to 1 centimeter, so 0.01 meters. And then, so we have a constant pressure difference. So that means that delta P1 is equal to delta P2. That doesn't change. It takes 30 seconds for a volume of water, so let's say that's going to be T1. T1 is equal to 30 seconds, so that's when water is being used. And then T2 will be when we're using the unknown fluid, so that's 75 seconds. And we want to find out the viscosity of the unknown fluid, so viscosity 2 is equal to question mark, and we know the viscosity of water, so that's viscosity 1 is equal to 1.8 times 10 to the negative 3. Okay, so we've got all our variables. So again, we're going to use, because we have time, we're going to use delta V over T is equal to delta P times pi r to the 4th over 8 times viscosity times L. And you're going to rearrange this for something that stays the same again, because you have to rearrange this for something that stays the same. So delta P1 and P2 are the same. So we'll rearrange for delta P is equal to delta V 8 viscosity L over T pi r to the 4th. Okay, so that means that delta V1 times 8 times viscosity 1 times length 1 over T1 times pi times R1 to the 4th power is equal to delta V2 times 8 times viscosity 2 times length 2 over T2 times pi times R2 to the 4th power. Okay, so this is delta P1, delta P2, because we know that delta P1 is equal to delta P2. Okay, so we're going to cancel out what's staying the same. So delta V1, delta V2, 8. The length is the same. Pi is the same. Radius is the same. So we just got viscosity and the time on both sides. So that's so viscosity 1 over T1 is equal to viscosity 2 over T2. So we want to find out what viscosity 2 is. Viscosity 2 is equal to viscosity 1 times T2 over T1. So viscosity 1 was 1.8 times 10 to the negative 3 times T2, which is 75, over T1, which is 30 seconds. So that will give you 4.5 times 10 to the negative 3. Okay? Cool. So that I went through that one a bit fast because it's quite similar to the last one. Okay, now we have a diffusion one. A drop of ink is deposited into a large volume of motionless water and initially has a radius of 1 millimeter. So initially our radius is 1 millimeter, okay? But then after 2 seconds, the ink has diffused and diffused further into the water. So now the radius of the ink is now 3 millimeters. It's a wonky circle. Okay, so now the radius is equal to 3 millimeters. So how far has it traveled? So it's the distance that, the average distance that the ink has traveled is going to be this distance here. So that's going to be 2 millimeters. So x RMS, the average distance traveled, is equal to 2 millimeters, which is equal to 0.002 meters. And we know that the time was equal to 2 seconds. So we can calculate the diffusion constant. So this is a two-part question. So we need to first calculate the diffusion constant of this ink and the water. And so D is equal to x squared over 2 times T. So x was 0.002 squared over 2 times 2, which is 1 times 10 to the negative 6 meters squared per second. Okay, so now we know the diffusion constant, and then now it's another scenario. So now they're saying how long will it take for the ink to diffuse from a radius of 1 millimeter to 11 millimeters. So the average distance traveled will be from 1 millimeter to 11 millimeter, so that's 10 millimeters. So now I'll just use different color. So now the x RMS is equal to 10 millimeters, the average distance traveled, and we want to find out the time. Okay, and the diffusion constant will be the same. So D is equal to 1 times 10 to the negative 6 meters squared per second. Okay, so T will be equal to x squared over 2 times D. And so 10 millimeters is 0.01 meters, or you could say it's 10 times 10 to the negative 3 meters, okay? As long as you convert it into meters, it doesn't matter which one you use, so I'll just use 0.01 squared over 2 times 1 times 10 to the negative 6. And that will give you 50 seconds. Okay, any questions? Okay, cool. All right, thanks very much. I'll see you guys next week, and good luck for the terms test on Saturday. Yeah, just try and don't get too hung up on hubs, because some people just all they do is that paper before the test, and then they ignore all the other papers. So don't do that. Just try and keep it balanced the whole way through. Yeah. So good luck.